Hello everyone. In the last class, we discussed about what actually this manufacturing subject is, and then what are the different manufacturing process that we have in manufacturing, and how to convert that raw material which is of no use into a product of definite shape, definite size, better surface finish, and can be used to impart some functional requirement that it has. Okay, so we saw what are the different manufacturing process. Like casting, we have metal forming, then we have machining, we have welding, and we started our lecture about the casting process. We discussed what actually that casting process is. Nothing is like what we do is we have a raw material, we melt it, we pour that molten metal into the mold cavity. So mold cavity that is made by the pattern. We pour that molten metal and then it is allowed to solidify. Now after solidification, we take out the product by breaking the either sand mold or by separating that metal mold. So that is what that casting process is. We discussed about what are the different allowances that we have to give on the pattern. Like when that molten metal is poured, and it is the material property that it shrink, it shrink during solidification. It will contract. Now once it contracts, what we have to do is, like once it contracts during solidification, so we will get the product which will have the dimension which will be less than the desired dimension that we want. So what we will do is, in case of pattern, what we do, we give some allowances on the pattern. Allowances means in some case we make the pattern bigger, in some case we make the pattern smaller, so that after solidification we get the product which is of required dimensions. Okay, so what are the means? We discussed about the different allowances that we give on the patterns. Like we give the shrinkage allowances. We discussed about the machining allowances, because we know that the product that we get by casting, obviously its surface finish is not that much good. So but in some cases, but in most of in the component, but we require very good surface finish, and that we do not get in casting. So what we give, what we do is we give a extra layer of that materials. We give the allowances on the pattern. Allowances means again we are making the pattern bigger, so we'll get some extra material on the product, which will be removed by the subsequent machining operations. Okay. Again we discussed about the draft allowances. So in draft allowances, what we do is, like, we make the surface into an inclined one. Why it is necessary to make that surface, vertical surface, into inclined one? Because once we keep the pattern into the mold, now once we have made that mold, now while withdrawing that pattern from the mold, what happened that if it has the vertical surface, it will remains in contact. It will remains in contact with the mold till we take out that pattern. So it remains in contact. So what will happen is, like, due to some machine error, due to the vibration or the person who is doing that, who is withdrawing the pattern from the mold, what will happen is it will damage your mold cavity. Right? It will damage your mold cavity. So to avoid the damages to that mold cavity, what we do is, in case of that vertical surface, we make that surface into inclined one by say 1 to 5 degree. In case of that external surfaces, right? So what will happen, once you just lift that pattern from the mold, you will have some gap between the pattern and the mold. So once it will have gap, again your pattern is not in contact with the mold cavity, and you will get the cavity without any damages. So obviously you are getting the cavity without any damages, means your product will be free from the defect, right? So this is why we give this draft allowances. We discussed about the distortion alliances. So in distortion alliance, what happens is, like, if we have a thick component and the thin component, right? So thin component which is joined with that thick component. So during solidification of that, say, T shape, okay. So what happens is, during solidification, due to the differential shrinkages at different location, what will happen is, like, there will be that crack in that your product. So what we do, suppose if you are making that U shape, okay, if you are making the U shape, so due to that differential shrinkage, the leg of that U will be bent in that outward direction during solidification. So what we can do is, we will make the pattern whose leg is in that inward direction, so that after solidification you will get that vertical leg of U. So that is why we give that distortion alliances. Now again we discussed about that SSC alliances, and SSC alliances is like if we keep the pattern. So keep the pattern means after making that mold, what we do is we shake that pattern. Why it is necessary to shake that pattern? Because once you shake, it is the property of that sand, okay, which will adhere to your pattern. Okay, so which will adhere to your pattern. So what we will do is, like, we will shake the pattern so that the sand will be separated from your pattern. But during that shaking, what will happen? Your cavity will become, that larger. Your cavity will enlarge. So in that case, what we do is we make the pattern as smaller. So in case of SSC alliance, it's a negative alliance that we gave on the pattern. So we make the pattern as smaller so that after shaking, we'll get the required size of your mold cavity. Okay. So these are the different alliances that we discussed in the last class. And we also discussed, about how to find out, like how to specify that liquid shrinkages, how to specify that solidification and that solid shrinkages. So basically that liquid shrinkages is, specified by the percentage over volume. So we saw, like, we pour that molten metal into the mold cavity at pouring temperature, which is not at that melting temperature. Why? Because if we pour that molten metal at the melting temperature, so what will happen is, like, your molten metal will solidify somewhere in the passage, right? So once it is solidified somewhere in the passage, means it will not be able to fill that cavity. Your cavity is not completely filled. So in that case, what will happen is, once it is not completely filled, you will have the defect. Now, which type of defect you will have because of this? So you will have that mishran. So mishran is nothing but the non-filling of that some portion of your mold cavity. Why? Because you are pouring that molten metal at the melting point temperature, and it is solidified somewhere, in the passage, and it will restrict the flow of the molten metal into the cavity. So what we do is, we give some degree of superheat. Degree of superheat means we are heating that molten metal above its melting point temperature. Suppose for some material its melting point temperature is say 600. So we will pour that molten metal at 700 degrees centigrade, so that it will not solidify somewhere in your passage. Okay. So we pour that. Now once it starts solidifying, it is the property of the material that it will shrink. It will shrink. So what will happen? We are pouring the molten metal at the pouring temperature. Now it will start cooling. From that pouring temperature, it will reach to freezing temperature. So in that case, what happens is, what is happening is, like, there is a, the transfer of heat. Okay, it is cooling. Your molten metal started cooling. So your temperature of that molten metal will decrease from that pouring temperature to the freezing temperature. Now in that phase, there will be some shrinkages in your molten metal, and that shrinkages is called the liquid shrinkages. Okay. Now once its temperature reaches to freezing point temperature, your molten metal will start solidifying. Okay. So there will be phase change. Basically from liquid it will get, converted into the solid at the freezing temperature. So there will be, the cooling in the form of that latent heat. Right. Now again in that phase, what happens is, there will be shrinkages. There will be shrinkages in the molten metal. Now that shrinkages, what we call is solidification shrinkage. Now once it is solidified, once you have that molten metal in that solid form at that freezing temperature, again there will be cooling from that freezing temperature to the room temperature. So during this stage also, there will be some contraction in that solid, and that contraction is known as the solid contraction. Now we discussed in the last class that there are 3 stages of that contraction during that solidification. Now the first 2 stages of contraction, that is your liquid and solidification, is compensated by using a riser. We saw that, right? So riser is nothing but it's a reservoir of molten metal. Either we keep that riser on the top of your mold or in the side, right? So it can feed that molten metal from the top or from the side. So what we will do is, like, that liquid shrinkages and solidification shrinkages are compensated by using the riser and the last stages of that contraction in that molten metal is compensated by giving the alliances on the pattern. Alliances means making the pattern bigger or smaller in some cases, right? In some cases like sake alliances that we discussed. So we discussed about these are the very important thing, forget. You will get some question from this shrinkages. How to find out? So we discussed how that liquid shrinkages are specified in terms of volume. So volume means like if you have to make a casting of say cube casting of size say 40 mm. So we'll find out that volume of the cube. Okay, we'll find out that volume. Say the shrinkages alliances say 5%. So 5% of that volume. So they will tell you to find out the side of the cube after that shrinkages. Shrinkages may be liquid shrinkages or solidification shrinkages or the solid shrinkages. So they will tell you to find out either volume or the side of that different castings after that shrinkages. And we discussed that solid shrinkages are specified, say its temperature is decreasing from freezing point to room temperature. So how can we find out that shrinkages? We'll find out. So we know that once that there is a decrease in temperature, there will be the thermal strain in that material. Thermal strain will be given by that alpha into delta T, where alpha is your coefficient of thermal expansion and or contraction, and that delta T is the change in temperature. Change in temperature here it is from freezing temperature to room temperature. So by using this formula you can find out your thermal strain. Now once we know that thermal strain, we can find out the change in dimension. So solid contraction is specified or is given on the each dimensions. Okay, it is given on the dimensions. So suppose we have to make a cube, so on each dimension we'll give that solid shrinkages. So in this way you can find out the the volume, or you can find out the dimensions after contractions. So these are the things that we discussed in the last class. We also discussed about the pattern. We also discussed about what are the different materials that we have for pattern, and what are the different types of pattern. We discussed about the single piece pattern, which is which is the least expensive, simple one, and it should be in your it should be kept in your drag. Okay, it should have that one of its surface should be flat. Why? It will be easy to make that parting line or parting plane. Okay, so because if it does not have the flat surface, it will be very difficult to make that parting plane. So it is expected that your single piece pattern should have that flat surfaces in order to determine that parting plane. Then we discussed, so this single piece pattern cannot be used for a mold which are that much deep, which are very deep, because if it is deep, it will be very difficult to withdraw that pattern from the mold cavity. Now suppose we have we have to make a casting, we have some pattern which are of a very complex shape. So in that case what we will do? What we will do is like we'll split that pattern. A split means we will divide it into two halves, and what we will do, we will keep one half in the cope part, we'll keep the other part in the drag, and then by using that we will make the mold cavity. So that split pattern we discussed, it is used to make the cavity which are very intricate or which are very deep. Okay, we discussed about the match plate, we discussed about cope and drag for some handling, if there is some handling problem. So very last or very heavy casting we use that. Then we started the follow board pattern. Now you can see its figure in your slide on your screen. We'll discuss what actually that follow board pattern is. Now suppose if we have to make a cavity, obviously we make that cavity by using some pattern. Now for example, if your pattern have some of its section which are very thin, okay, very weak section it has. Now what will happen is, to make the mold, what we will do is we'll keep that pattern into the flask, and then we'll fill that flask with the sand, right? So once you fill that flask with the sand, and we'll apply the ramming force in order to get the required strength. Now if some of its section is very weak, so what will happen, that section will break during that ramming or during that compression of that sand. Now, how can we avoid that? How can we avoid that, that breakage of the weak section of your pattern? So what we will do is, suppose if you have a pattern of, say, something into this shape, right? So this is your thin section. This is thin, and something. Suppose this section 1 and this one 2. So these two section of your pattern is weak. Now how to avoid that breakage of that pattern, weak section of the pattern? Now in that case we'll use the follow board. What that follow board is? That board will use some. It will have. You can see the figure in your slide. It will have the same projection as that of your pattern, right? It will have the same projection of your pattern. We'll keep that board below that pattern, so that once you fill that flask with the sand and will apply the force, it will avoid the breakage of your weak section of the pattern. Okay, so we'll keep that board below this pattern, and then we'll fill that flask. Fill that flask with the sand, and we'll apply the ramming force in order to get the required strength. So in that case, what will happen? Obviously, this follow board will not allow to break the pattern. But some of you might be thinking that once you will remove this follow board and pattern, obviously we'll also have this cavity. So this is only to make, say, cope part. We'll keep that board below this pattern in the cope. Now once this sand, the flask with that sand gets the required strength, now we'll have to make the drag part. Okay, or either we'll make the drag and then we'll make the cope. So this is for the drag. Now once the drag part is made, we'll remove this board and we'll keep the flask over the drag, and then it is to be filled with this sand. Now again, to get the required strength of the cope, is it necessary to place that follow board again? No. Why? Because this sand which is near to that weak section will provide the required strength while making the cope part. So it is not necessary to make or to keep that board in making that cope part. The sand below that pattern, which is in that drag, will give you the required strength. So now again, that in cope, we'll fill that flask with the sand and we'll apply that ramming force, and then we'll remove that cope part, and then we'll remove the pattern, and we'll have the required cavity. Okay, you can see in your slide on your screen. You will understand that. So basically, this follow board is used to to avoid the breakage of the weak section of your pattern while making that mold cavity. That's all. Nothing more about it. Now after this follow board, we have the sweep pattern. Now we have the sweep pattern. What exactly that sweep pattern is? Sweep pattern. Again, you can see, this figure on your screen. Now, this sweep pattern is basically used to make that 3D casting, we can say, by using the 2D plate or something, by using that sweep, which is nothing but it's a, say, flat plate. Obviously, it will have the outer surface of that plate will have the shape that is required in your casting. Okay, so what we do is, like, we'll keep the sand in the flask or somewhere, right? then we'll keep that plate, and that sweep is connected to your spindle, and it will rotate at some RPM. Now once it rotates, it will throw out this end. So by using that 2D sweep, we are making the 3D cavity. Simple. Now why is it necessary? Because obviously because of the cost of that 3D pattern. Suppose if you wanted to make a bell, okay, obviously it's a very large, and to make that, obviously the cost of the pattern will be very high. So basically we are reducing the cost by using this sweep. So by using sweep, that is your 2D, we are making the 3D cavity or 3D casting. And the condition for with this sweep pattern is it is used to generate the axis symmetrical, shape. Obviously that is symmetrical, okay, such as bell shape and the cylindrical shape. Now the sweep pattern reduces the cost of your 3D pattern, as I said. By using the sweep, which is your 2D, we are making the 3D casting. Now this type of pattern is suitable for very large casting such as that bell, as I said that. Obviously, for making very large casting, the cost of the pattern will be very high. But here we are having the 2D sweep, which is connected to that spindle, which is rotated at some RPM. So during rotation, it will throw out the sand from that mold, and it will generate the cavity that is required. Okay, nothing more about it. So you can note down your important points from your, this slide. Now after this, so we discussed about the different types of pattern that we have. Now we'll discuss, again an important concept, core and core print. Now we'll discuss the core and core print. Now what actually that core and core print is. Now suppose in the first class we discussed about how to convert that raw material into that cube, which is of definite shape, size, and obviously better surface finish. So suppose by using that casting, we have this product, say this is your cube. So to make this cube, we require the cube pattern, which may be either of wood, plastic, or anything. So we'll require that wood pattern. By using that pattern, you will make that cavity in your mold. You will make the mold. Once you have the mold, we have some raw material, say some raw material. This is your raw material. You will melt it, you will pour into that cavity, and it is allowed to solidify, and after solidification you will have the casting. Now, but suppose if we have to make a cavity in the casting, suppose if we require the hole, if we have to make a hole into this cube, what will you do that? The question is, for solid, we require that solid, that pattern. Now if we have to make the cavity into your product, what we will do is, we will use the core. So basically this core is used to make the cavity in your casting. It's simple. This core is used to make the cavity in your casting. Now the question is, how to make that? By using that core. So it's a kind of pattern, right? So suppose if we have so this is your core, this is your drag, and this is your mold cavity, this is your mold cavity, right? Obviously, to pour that molten metal, we require some passage, or it is known as the gating system. Okay. So this passage we require. So this is your gating system. We'll discuss about it, how to design that gating system. Okay. So this is your mold cavity. The top part is what we call the core. The bottom part is known as the drag. This is your passage through which that molten metal is to be poured in your mold cavity, and obviously it will fill that cavity. Now, to make that cavity in your casting, you will have to place the core in that mold cavity here, right? So what we will do, we'll place the core here, right? We'll place the core. We'll place the core here. Somewhere here. We'll place that core in that mold cavity. We'll place that core in the mold cavity, and now the cavity is filled with that molten metal. It is to be filled with that molten metal. So obviously that molten metal surrounds that core. Now the molten metal is filled in that, your cavity is filled with that molten metal, and we have the core in the middle of your mold cavity. Now it will solidify, this molten metal will solidify, and once it is solidified, we'll break that mold and we'll withdraw that core from that solidified molten metal. So once you will remove that core, obviously you will have cavity into your product. So again, this core is nothing but it's a pattern which is to be placed into your mold cavity in order to have the cavity in your casting, in order to get the cavity in your casting. So core is used to make the cavity. This core is used to make the cavity in the casting. Now we'll discuss, the force that will act on the core. So now here we have this cavity which is filled with that molten metal, and in that middle we have the core. Now obviously we know that the buoyancy force will act on the core, because this core is placed in that middle of your cavity, and obviously the buoyancy force will act on the core. Now what will be the magnitude of that buoyancy force? So we know that buoyancy force is nothing but the weight of the liquid that is displaced by the core in this case, or some body, weight of the liquid that is displaced by some body. So here we have this core. So weight of the liquid displaced by this core is nothing but your buoyancy force. So buoyancy force at B will be equal to the weight of the liquid displaced by the core, which will be rho G into V. Now what is this rho? So it is the weight of the liquid displaced by the core. So weight of the liquid. So obviously that rho is nothing but the density, and it will be the density of your molten metal. So rho M. G is your acceleration due to gravity, 9.81, and V is the volume of the core. Okay, so rho m will be equal to the density of molten metal, G, you know, 9.81, and V is volume of the core. So this is the buoyancy force that will act on your core by Archimedes principle that we know. Now at the same time, obviously this core will have some weight, obviously, and the direction of that weight will be in that downward direction. Obviously that weight of your core will act in this direction. So this is the weight of your core, and this is your FB, that is the buoyancy force that is acting on the core. At the same time, this core will have some weight which acts in the downward direction. So if we have to find out the net buoyancy force, we'll write down the net buoyancy force FB net will be equal to the weight of liquid displaced by core minus the weight of core. So this will be your net buoyancy force that will act on the core. So weight of the liquid displaced by the core is your rho m GV, where rho m is the density of that molten metal, G is the acceleration due to gravity, and V is the volume of the core, minus weight of the core. So weight of the core will be rho, which is the density of your core, multiplied by G into V, again the volume of the core. So this is your FB net, that is your net buoyancy force that will act on the core. And this is very important, you will get some question by using this formula. You will get some question in GATE. So in this way we can find out the net force that acts on the core, net buoyancy force, obviously. So you might be knowing what exactly that buoyancy force is, obviously. If you don't know, means just go through the fluid mechanics books, you will get that. Okay, so this is the net buoyancy force that acts on the core. So in this way we can find out the net buoyancy force. Now the question is, what is this core print? What is this core print? Now core is used to make the cavity in the casting. It's a kind of pattern, and the core print. Now to place that core in the cavity, obviously it has to be supported. Obviously, then only it will, it will remain in the position in the cavity. It requires some support to be in position in that mold cavity. Okay, and that support is given by the core print. So here you can see, this is the recess that is given in your mold. Okay, and your mold is nothing but the core print. Now how will you make that cavity or recess in the mold? By giving that on the pattern. So we discussed, pattern is the replica of the shape to be cast. Okay, its shape will be same as that of your casting, but its dimension may be different. Okay, so we give some provision to that pattern. So obviously it will form the cavity in your mold that will give the support to the core. So this core print will give you the support for this core to be in position to keep this core in position in the mold cavity. Now obviously there will be some limitation. It's not like that, means if the weight of the core is say 1000 Newton and this core print will withstand that 1000 Newton. Obviously there will be some obviously the value of the force that this core print can withstand. If you exceed that limit, obviously we will have to give the other support to keep that core in the mold cavity. Now what exactly that, the value of that, we will see that. So if this F net, that is your FB net buoyancy force, okay, if FB net is less than or less than equal to that 3.5 of that A, where A is the surface area of your core print, where A is the surface area of that core print, and it is so 3.5. If FB net is less than 3.5A, or I can say FB minus this 3.5A is your unsupported load. Okay, so if that unsupported load is less than or equal to say 0, in that case we do not require the extra support in order to keep that core in position in that mold cavity. Now if that net buoyancy force is greater than the 3.5 times the total that surface area of your core print, in that case we require the extra support, and that extra support is given by using the chaplet. Okay, so that is the purpose of the chaplet. So this is your chaplet. So we have to use that chaplet in pairs. So if that net buoyancy force is less than that 3.5 times A, then where A is the surface area of your core print, in that case we do not require this core print. Okay, we do not require this chaplet. We do not require chaplet. But if this net buoyancy force is greater than the 3.5 times A, or this FB net minus this 3.5A is your unsupported load. This is your unsupported load. And if it is greater than 0, this unsupported load is greater than 0, in that case we require some extra support, and that extra support is given by chaplet. If this unsupported load is greater than 0, then this chaplet is used. So this chaplet is used to support that core, to keep that core in position in that mold cavity. When this core print, that is the this core print you can write down the this is given in mold to support the core. So when this core print is not able to support that core, we'll use that chaplet. So chaplet is used to support that core, to keep that core in position in that mold cavity, and as an additional function, obviously it is used for that directional solidification. Directional solidification. As an additional function, it is used for that directional solidification. We'll discuss that directional solidification when we will discuss the chills. Okay. So this is all about that core print and the chaplet. Core is used to make the cavity in the casting. So once you keep that core in the cavity, obviously on that core, some buoyancy force will act in the upward direction. Okay. And the value of that buoyancy force will be the weight of the liquid displaced by this core. So net buoyancy force will be the buoyancy force in that upward direction minus the weight of the core. FB net, rho m JV minus rho c JV. Rho m is your density of that molten metal and rho c is the density of your core. So in this way we can find out the net buoyancy force. Now when this net buoyancy force is less than or equal to 3.5 times A, in that case we do not require any extra support. So whatever the required support is given by the core print. So core print is nothing but that recess given in the mold to support the core. Obviously to keep it position, obviously we'll have to give some support to that core. Now when that unsupported load is greater than 0, this is your unsupported FB net minus 3.5 times A. When this unsupported load is greater than 0, in that case we require some extra support, and that is given by the chaplet. Now the material of that chaplet is same as that of your molten metal. Okay, it is assumed or it is believed that the heat present in your molten metal will melt your chaplet. It will mix with that molten metal and we'll get that product. Obviously that chaplet is to be free from that moisture, otherwise it will have some defect in your casting. It will have moisture, it will have the blowholes. So obviously you have to clean that chaplet before keeping that into your mold cavity. The material of that chaplet is same as that of your molten metal, so that heat present in the molten metal will melt your chaplet. It is believed that, right? So we discussed about the core and core print and then chaplet. And so the main function of chaplet is to support that core, but as an additional function it is used for directional solidification. We'll discuss about it when we will discuss the chills. Now you can see, some of the important points regarding this core and core print in your slide, which is on your screen. Which is the first point where we have a core is used to make the cavity and hollow projection in the casting that we discussed here. Now, what are the different properties that it should have? It should have high collapsibility. It should be free from moisture. Obviously, it should be free from moisture, because if there is a moisture in your core, so what it will do is, obviously it will produce the casting which will have some defect, like blowholes. Okay. High collapsibility. Why it should have high collapsibility? Collapsibility is nothing like to break that core. It's nothing like that. Collapsibility is like when we keep that core in the mold cavity, here we are keeping that core in the mold cavity, and it is surrounded by that molten metal. Obviously, from all the side we have this molten metal here in that cavity. Now, we discussed that during solidification, this molten metal will shrink. It is a property of the material that it will contract during solidification. Now the contraction, obviously the contraction in that molten metal will be towards the center. So high collapsibility means ability of that core to allow contraction in that molten metal during solidification. That it means collapsibility. Collapsibility is not means like is the ability to break that core. It's not like that. Collapsibility means it is the ability of the core, it is the ability of the material of the core to allow contraction in that molten metal during solidification. So once it allows, then only obviously we'll have the casting which will be free from defect. Otherwise, if this core is not allowing the contraction in the molten metal, we'll have the hot tear. Will have the crack in the casting during solidification. So that is why obviously this core material should have high collapsibility. Collapsibility means it should allow contraction in your molten metal during solidification. So it should have high collapsibility. This is the first property of your core. Second, it should be free from moisture, because the moisture present in that molten cavity will give you some defect in your casting, like blowholes. Then the third is able to withstand the high temperature. Obviously, ability to withstand the high temperature means it should have high refractoriness. Refractoriness is the property of either the, we can say, mold or the core. Here we have the core, so it is the ability of the core to retain its strength and hardness at elevated temperature. Retain its hardness means obviously if we are increasing the temperature, obviously the hardness and the strength should not get reduced. Okay, so it should be able to withstand the hardness and strength at elevated temperature, at very high temperature. Okay, so obviously the core material should have high refractoriness. Then the last point is should have high strength to withstand the self weight and buoyancy force. Obviously it should have the sufficient strength to withstand that buoyancy force. Obviously that we discussed here, that is acting on your core in that upward direction. It should have sufficient strength. Core print we discussed, it is used to give the required support to that core. So cavity made in the mold for locating, positioning and supporting the core is known as the core print. It is the main purpose of that core print, and it is this core print or that cavity or that recess is made by using the pattern. So this extra projection, that cavity that you are seeing in that mold is made by giving that projection on the pattern. Okay, so suppose if we have to make a cube, so obviously your pattern, the shape should be same as the shape of the pattern should be same as that of your casting. So say this is your pattern, obviously we will have the cube pattern, and to locate the core, we'll have to give some projection on that pattern here. Okay, here's something on the both the side, right? So what we will do is, once you will keep that pattern in the cavity, we'll fill that with the sand, we'll apply the ramming force, and then we'll remove that pattern, so that you will have this extra, that you will have this cavity in the mold, which will be used to give the support to that core. So it's nothing but it's a core print. It's a recess or cavity in your mold to give the support. Now once it is not sufficient, if the force, this buoyancy force is very high, in that case, if that core print is not able to give the required support, we'll use chaplet that we discussed. We discussed that its material should be same as that of your casting material. So chaplet, you can see some important points about the chaplet in your slide, which is on your screen. Its function is to act as an additional support for supporting the unsupported load. Obviously, for it is used to give the extra support, that is to support for that unsupported load, which is F net minus that 3.5 times A. Okay. Now chaplet material should be same as that of the casting material. As I said, its material should be same as that of your casting material, so that what will happen is, like, the heat present in your molten metal will try to melt that chaplet, and so it becomes a part of your casting. but it is practically it is not true, because that heat will not completely melt your chaplet. Okay, so obviously it is not required to have that chaplet, because again that chaplet should be clean from moisture to avoid the defect. Then for 1 Newton of unsupported load, 29 mm square cross-sectional area of the chaplet must be used. So we discussed what that unsupported load is. So for 1 Newton of that unsupported load, we'll have to give the 29 mm square cross-sectional area of the chaplet. Okay, so for 2 Newton, we'll use 2 into 29. For 3, 3 into 29. That much cross-sectional area your chaplet should have to support that unsupported load. That is the condition. And its additional function is directional solidification. So now we'll discuss what actually that directional solidification is. So the additional function of that chaplet is directional solidification, and now we'll discuss that what exactly that directional solidification means. So we'll discuss what exactly that directional solidification. Now suppose if we have to make a casting of L shape, okay, if we have to make a casting of say L shape, okay. So this is the L casting that we have to make, and obviously it is to be filled with some molten metal. This cavity, obviously you require that cavity of L shape, and that cavity is to be filled with the molten metal, that is your required material of your casting. So say it is now this cavity in your mold is completely filled with the molten metal, with the material that you wanted to cast. Now obviously during solidification this liquid molten metal will contract, and to avoid that contraction or shrinkages, say we are using 2 riser. So this is your riser. Okay, so this is your say riser. This is your riser. So again that after filling the cavity, your riser should get completely filled, so that once that molten metal starts solidifying, the extra molten metal from that your riser will supply that molten metal to avoid that contraction. Okay, so here we have this mold cavity which is completely filled with that molten metal, and to avoid that shrinkages we are using the 2 riser, right? Now what I am doing is, like, we are dividing this L shape into 3 zones. Say this is your zone 1, say this is your zone 2, and say this is your zone 3. Now the first thing is the volume of the molten metal that is present at the corner will be greater than the molten metal present in the zone 1 and zone 2. Okay, so obviously the molten metal in the zone 2 will take the extra time than zone 1 and zone 2 to solidify. What I said is, the molten metal present, the volume of the molten metal present in the zone 3 will be greater than the zone 1 and zone 2. So when that volume is greater than zone 1 and zone 2, so obviously it will take the extra time to solidify than zone 1 and zone 2. So the solidification time of molten metal in zone 3 will be greater than the solidification time of the molten metal in zone 1 and zone 2. So the molten metal present in the zone 3 will solidify after the molten metal in zone 1 and zone 2 has solidified. Now, if the molten metal starts solidifying in zone 1 and zone 2, and if it obviously it will contract, there will be shrinkages, so extra molten metal will be supplied by using this riser. And as I said that this zone 1 and zone 2 has solidified before the zone 3. Now obviously it will take the greater time than zone 1 and zone 2, and we do not have the riser present at the corner to compensate the shrinkages that is taking place during solidification. Why? Because the zone 1 and zone 2 has already solidified and we do not have that extra molten metal. So this zone 1 and zone 2 has already solidified, so obviously the molten metal from this riser will not be able to feed the shrinkages in the zone 3. Okay, and we do not have the riser at the corner. So the actual condition should be the zone 3 should solidify before zone 1 and zone 2. Okay, so once that zone 3 has solidified before zone 1 and zone 2, so obviously that riser will supply the or will feed the extra molten metal that it requires to avoid the shrinkages. So how will you solidify the zone 3 before zone 1 and zone 2? This is the thing that we actually want. Okay, we have to solidify the zone 3 before zone 1 and zone 2. Why? To avoid the shrinkages. Shrinkages means the cavity. The cavity that is formed in your casting because of that insufficient molten metal that we are not getting from riser. Okay, so how will you or what can we do to solidify the zone 3 before that zone 1 and zone 2? Okay, so we cannot, we cannot increase that volume out. Okay, so what we can do is we can increase the surface area. Okay, we can increase the surface area so that obviously there will be more transfer of heat from that surface area and your zone 3 will be solidified before zone 1 and zone 2. So what we will do is we'll place some metallic plate, okay, at the corner, which will have, this is your metallic plate. Why we are using this metallic plate? To increase that surface area, and this metallic plate will have very high thermal conductivity. Okay, so to solidify the zone 3 before zone 1 and zone 2, we are using this metallic plate. Obviously, we are using the metallic plate to increase that surface area so that zone 3 will solidify before zone 1 and zone 2. Okay, and this metallic plate should have very high thermal conductivity. Why? In order to transfer the heat. Obviously, the plate which is having very high thermal conductivity will transfer more heat. Okay, So what we are doing is we are trying to transfer the heat, okay, through by using this plate, so that this zone 3 will solidify before zone 1 and zone 2, so that you will get your casting which will be free from the defect, which is your shrinkage defect here. Okay. So this metallic plate that we are placing at the corner is known as chills. Chills. Okay. So this chills is used for the directional solidification. Directional solidification. Directional solidification means we are solidifying the zone 3 before zone 1 and zone 2 in order to avoid it from the defect, so that the molten metal will start solidifying from at the corner toward that riser, so that you will get the casting free from the defect. So we are trying to solidify this molten metal in a particular direction. Okay, progressive, in a progressive way, to avoid the defect. Now obviously in order to decrease its solidification time, we are using the metallic plate, which is having very high thermal conductivity. So how can we increase that transfer of heat? By increasing that surface area. Okay, so by increasing that surface area, by using a plate which is having very high thermal conductivity, we are transferring the more heat, so that the molten metal present in the zone 3 will solidify before the molten metal present in the zone 1 and zone 2. Okay, so that this riser will be able to feed the extra molten metal which is required to avoid the defect in your casting. Okay, so as an additional function, that chaplet can be used for that directional solidification. Okay, so but the main function of that chaplet is to give the extra support to that core. Okay, but as an additional function, it is used for directional solidification. But the main purpose of using these chills, which is a metallic plate of very high thermal conductivity, is used for directional solidification. Okay. Now we'll solve one question from that buoyancy force, one numerical. Now the question you can see on your screen. This question was asked in Mechanical Engineering 2013 for 2 marks, and the question is, an aluminium alloy of density 2600 kg per meter cube casting is to be produced. So aluminium alloy casting is to be produced. A cylindrical hole of 100 mm diameter and 100 mm length is made in the casting using the sand core. Okay. So we have to make a aluminium alloy casting. In that, we have to make a cylindrical hole of 100 mm diameter and 100 mm length by using the sand core. So the material of that core here is sand, whose density given is 1600 kg per meter cube. We have to find out the net buoyancy force in Newton, which is acting on the core is. So we have to make a aluminium alloy casting. So that rho m is 2600 kg per meter cube, and in that casting we have to make a cylindrical hole. We have to make a cylindrical hole of diameter 100 mm and length is 100 mm. How we are making that cylindrical hole? By using the sand core of density 1600 kg per meter cube. So we have to find out the net buoyancy force, that is FB net, which is acting on the core. This we have to find out. Okay, how will you find out? So we know this net buoyancy force is nothing but that rho m GV minus rho c GV. Or directly I can write now. This is rho m minus rho c into GV. Okay. So this is the net buoyancy force acting on the core, which is the weight of the liquid displaced by the core minus the weight of your core. So this is the net buoyancy force which is acting on your core. So rho m is 2600. Rho m is 2600. So 2600 minus rho c is 1600 into acceleration due to gravity g, we know 9.81 into, so this density is given in kg per meter cube. So obviously we will find out this volume in meter cube. So this volume we have to make a cylindrical hole. So cylindrical hole, for cylinder its volume is pi by 4 d square h. So pi by 4 into 0.1 square into 0.1, because diameter of that hole required is 100 mm and its height is 100 mm. So directly just put that value, pi by 4 into 0.1 square into 0.1. Okay, you'll get some value, 7 point something. Okay. So you will get 7.70 Newton. So this much, you know, the net buoyancy force that is acting on your core. And this buoyancy force is to be supported by the core plate that we discussed. Okay.
What's this? Just अभी आया। अच्छा।